This is an introduction to the association of intermolecular properties with some macroscopic functions of molecules. And this is captured in what we call the Clausius-Clapeyron Equation. So we will start then by reviewing the information that we covered in class. If you already know this information, you may skip and go directly to solve the problem. So in this equation, the idea is to associate the vapor pressure on the y-axis with the temperature on the x-axis. And as we can see here, for molecules that have strong intermolecular forces like water, indicated by the blue trace, the vapor pressure increases exponentially as a function of temperature. Similarly, for ethanol, in which the intermolecular forces are hydrogen bonding still but weaker, we see that the vapor pressure is going to be a little bit higher at a given temperature, as indicated by the arrow over here, the red arrow. And if we continue with this trend, when we consider diethyl ether, which has even weaker intermolecular forces, mainly dispersion forces, then the vapor pressure is even higher. So what we can see from this trend is that at a given temperature, the molecules that have the weaker intermolecular forces, such as diethyl ether, have the higher vapor pressure. So as we can appreciate that from the dashed line that is indicated by the cursor. We can also associate or observe from these traces the boiling point. Boiling point is defined as the temperature at which the gas phase and the vapor phase are in equilibrium. And if we set the atmospheric pressure at 660 torr, we can see from the line here that the intercept of each of the traces corresponds to the boiling point of diethyl ether, ethanol, and water. And again, those that have the weaker intermolecular forces are the ones that will be boiling at lower temperatures. The last component from this behavior has to do with how quickly the vapor pressure increases. As we can see in diethyl ether, it increases very rapidly. That indicates that the heat of vaporization is low. On the other hand, a substance like water takes much longer, more energy to increase its vapor pressure as a function of temperature. This behavior can be captured mathematically as well, using a relationship like the one that appears on the screen, in which we can see that at two different temperatures, if we know the heat of vaporization, or delta H sub vap, we can associate that with the vapor pressures P2 or P1 at the corresponding temperatures. You get to choose whether you would like to use a qualitative approach like the one on the left side in the graph, or a quantitative approach as the one on the right side described by the mathematical equation. So now that we have actually looked at these relationships, we have a problem that I encourage you to solve first on your own, and then you may want to compare your solution with my solution. The problem reads as follows. We have two substances, ethanol and N-propane. The questions are, which one has the lower vapor pressure at a given temperature, the lower enthalpy of vaporization, the lower boiling point? And once you have thought about these answers, sketch in the same graph the vapor pressure versus temperature for these substances. Indicate their boiling point as well. So take a few minutes to figure out a plan, solve the problem, draw your sketch, and then compare your answer with my answer. So the way to solve this problem we will start by considering the nature of the intermolecular forces for each substance, or the two substances that we have here. We will associate such forces with vapor pressure, the enthalpy of vaporization or heat of vaporization, and the boiling point. And then we use the Clausius-Clapeyron equation to predict the graph that we are asked to do. So let's begin then by looking at the intermolecular forces of ethanol and N-propane. And something I like doing when I'm solving these problems is to draw the structure in a so-called three-dimensional space so that I can understand the nature of the intermolecular forces, and also look at the types of components in the molecule, so it's possible to identify whether the molecule is going to be polar, non-polar, or hydrogen bonding, or not hydrogen bonding. So for ethanol, what we're going to have is a carbon with 3 hydrogens bound to another carbon, which is bound to 2 hydrogens, an oxygen, and the oxygen is also bound to a hydrogen. And this oxygen has 2 lone pair of electrons. Immediately we can identify that this type of arrangement leads to hydrogen bonding. So on the other hand, when we draw the structure for N-propane, we will start 1 carbon with 3 hydrogens, 1 carbon with 2 hydrogens, and the last one is another carbon with 3 hydrogens. We identified that this molecule is non-polar, and in fact the only forces that will be present in this case are dispersion forces. We know that dispersion forces are weaker than hydrogen bonding forces. Therefore, we can start associating the relative magnitude of these 2 forces with the vapor pressure. We know that vapor pressure is going to be lower for those molecules that have strong intermolecular interactions. So in this particular case then, it's going to be that one corresponding to ethanol that has the lower vapor pressure. If now we look at the part B, the lower enthalpy of vaporization, or delta H VAP, we can imagine that that molecule or substance that has the ability that requires more heat to be able to become or go into the gas phase is the one that is going to have the higher energy of vaporization, which in this case will correspond to this one here. And the lower energy of vaporization would be then that one corresponding to N-propane. For boiling point, again, the one that has the weakest intermolecular forces is the one that is going to boil first. So therefore, in this particular example, is going to be N-propane that we will boil first. And in fact, if we wanted to compare this with the information from the literature, which is not required for this problem, but it's also good to check if the information is available, we can see that the delta H of vaporization for ethanol is 38.56 kilojoules per mole, and that one for N-propane is 1904 kilojoules per mole, consistent with what we found here, that the lower is the one for N-propane. And for boiling point, If we consider the boiling point of these two substances, we see that for ethanol is 78.5 degrees Celsius, while for N-propane is minus 42 degrees Celsius. Consistent with what we were saying, that the lower boiling point is for the N-propane, which is right here. So we are also asked to draw a graph, and this graph has to capture the information of the relationship between the boiling point or the vapor pressure and the temperature. So for that, what we will do then is we'll use this information to draw a graph in which we draw on the y-axis vapor pressure, Vp, and then on the x-axis we're going to have temperature. And we know that the boiling point represented at 1 atmosphere is going to be minus 42 for N-propane. We'll make that red. And for ethanol, we're going to make that green. It's going to be 78.5. So we can assign then these temperatures as minus 42 degrees Celsius, and this one will be corresponding to 78.5 degrees Celsius. And this in general represents the behavior that we anticipate of having for these particular substances. We also noticed that because the delta H of vaporization is smaller for N-propane, the rise with temperature is much faster than the rise for the N-propane, which is more slow, represented by the green slope that we have here. And with that graph, this is sufficient to answer the question that you were asked. This is the end of the problem.